Every 40 seconds, one person in the world dies from cardiovascular disease. Every day, thousands of people in transplant queues learn that a donor organ has not been found for them. Their lives are a waiting game, a wait for a miracle that, for many, never arrives. The human body is a perfect mechanism, yet tragically fragile. Its components wear out, fail, and unlike a machine, we cannot simply order a new part from the factory. Or can we now? For centuries, we have learned to repair the body, stitching wounds, setting bones, removing diseased parts. The 20th century gave us transplantology, the miracle of transferring organs from one person to another. But this miracle comes at a dark price: the necessity of one person's death to save another, and a lifelong battle of the immune system against the foreign organ using heavy medications. Today, we stand on the threshold of a new era, an era where we stop repairing and start recreating, an era where we no longer need a donor because we ourselves become the material for creating a new part of ourselves. This is not science fiction. This is bioprinting. And we are not just talking about printing skin or cartilage. We are talking about the holy grail of regenerative medicine, about the world's first heart created from a patient's own cells. Section 1. Project Heart: Architecture of Life. To understand the scale of this breakthrough, we must first grasp the complexity of the problem. The heart is not just a muscle. It is an incredibly complex, multi-chambered pump composed of dozens of cell types working in perfect harmony. It has its own electrical system for generating impulses and, most importantly, a complex vascular network. You can print a heart scaffold. You can even seed it with living cells. But how do you make them live? How do you deliver oxygen and nutrients to every cell deep within the three-dimensional structure? Without vessels, arteries, veins, and capillaries, the organ simply dies from necrosis within hours. That is why the news that came in April 2019 from Israel rang out like thunder on a clear day. A team of researchers from Tel Aviv University, led by Professor Tal Dvir, achieved the impossible. They announced that for the first time in history, they had 3D printed a living, vascularized, that is, permeated with blood vessels, heart, using only the patient's own biological material. This was not just a model, it was a living organ that pulsed. Section 2. Recipe for bioink: How to print yourself. How did they do it? The process is as ingenious as it is complex. Step 1. Material collection. The researchers took a small sample of fatty tissue from patients, known as the omentum or greater omentum. This is the simplest and safest way to obtain two key components at once. Step 2. Separation. In the lab, this sample was divided into two fractions: cellular and extracellular. The extracellular fraction is the extracellular matrix, or ECM. This is essentially the natural glue or scaffold that holds cells together. This material was processed into a personalized hydrogel. It became the base for the bioink. The cellular fraction consists of the patient's fat cells and other cells. Step 3. Reprogramming. The obtained cells underwent an astounding transformation. They were genetically reprogrammed, reverting to the state of induced pluripotent stem cells, or iPSCs. These are a blank slate, cells that have not yet decided what they will become, from which any tissue can be grown. Step 4. Printing. Next, the bioprinting machine entered the picture. This is not an ordinary 3D printer with plastic. It operates with two types of inks. Structural ink, the same hydrogel created from the patient's matrix. The printer built the precise 3D architecture of the heart layer by layer, including all chambers and vessels. Cellular ink.
Stem cells programmed to differentiate into two types: cardiomyocytes, heart muscle cells, and endothelial cells, cells that line blood vessels. The printer methodically, layer by layer, applied the scaffold and immediately populated it with the appropriate cells in the right places, creating chambers from cardiomyocytes and laying vessels from endothelial cells. The result? After a few hours in the bioreactor, there was a mini-heart, about the size of a cherry or a rabbit's heart. It had distinct ventricles, atria, and major blood vessels. And, most importantly, it was living. The cardiomyocyte cells began to spontaneously coordinate and contract. This heart beat. Section 3. Reality and Horizons. Burden of the Creator. The printed heart from Professor Dvir is not yet ready for transplantation. It is too small. Though it beats, its contractions do not yet have the strength needed to pump blood throughout the body. It is an infant that needs to be grown and trained. The scientists face titanic challenges. Scaling. How to print a full-sized human heart and keep it alive during the hours-long printing process. Maturation. How to make billions of new cells work as a single orchestra. How to train the heart to beat strongly, rhythmically, and efficiently. For this, the organ is placed in special bioreactors, where it is trained by simulating real blood flow loads. Full vascularization. Printing major vessels is one thing, but how to create the finest capillary network that nourishes every millimeter of tissue? Despite these challenges, the Tel Aviv University breakthrough changed the paradigm itself. It proved it is possible. We are talking about a future where a patient with heart failure comes to the hospital, undergoes a biopsy, and in a few weeks receives a new, biologically identical heart printed from their own cells. A heart that their immune system will never reject. A heart that requires no donor. And this applies not only to the heart, liver, kidneys, lungs. We are already printing corneas that restore sight and skin for treating burns. Here we approach a fundamental idea that is both thrilling and terrifying. We stand on the threshold where we create not machines, but biological copies of ourselves on a 3D printer. We shift from the role of passive observers of evolution to active architects of life. We take on functions that for millennia were attributed to nature or gods. The Israeli mini-heart is not just a medical artifact. It is a symbol of a new era where technology and biology merge into one, posing the central question: if we can print any part of ourselves, are we ready for the responsibility that comes with this power?